In the next few minutes, I'll show you what tool use actually is, why every modern model is fine-tuned for it, the JSON contract that lets a text generator emit a function call without hallucinating, how multi-step and parallel calls work, what happens when a tool fails, and the new open standard called MCP that's quietly turning every API on the internet into something a language model can call directly. Welcome to Concept Stack. We produce one concept a day, and each one stacks on the last, building the framework for AI together. Let's dive into tool use. Last episode, we covered RAG, the architecture that retrieves relevant chunks and stuffs them into the prompt. RAG works, but it's system-driven. The pipeline runs the same way for every query, whether or not the user actually needs retrieval. Tool use is the opposite. The model itself decides, should I just answer from what I know, search a database, call an external API, run a code snippet, or chain several of those together? It changes the model from a passive text generator into something that can act. That's what makes every modern AI assistant, every agent, and every coding tool possible. Mechanically, tool use is a three-turn loop. The developer registers a list of tools, each one a name, a description, and a schema for its arguments. When the user sends a message, the model can either answer directly or, if it decides a tool would help, emit a structured call instead, naming the tool and supplying the arguments. The runtime executes that function, captures the result, and feeds it back into the model's context. The model reads the result and generates the final answer. The user only sees the answer. Everything in the middle is invisible. But here's the thing. The model is generating exactly the same way as ever, one token at a time. So how does it not just hallucinate the call? How does the runtime know what's a tool invocation and what's a normal reply meant for the user? The answer is two layers, both invisible to the casual user. First, every modern model has been fine-tuned during the post-training phase from episode 7 to emit tool calls as structured JSON in a separate field, not as free text. Second, at decode time, providers apply something called constrained or structured decoding. The model still generates token by token, but the set of legal next tokens is restricted to ones that produce a valid JSON object matching the registered tool's schema. The tool name has to be one the developer registered. The argument types have to match. Required fields have to be filled in. The model can decide to call the wrong tool. That's a planning mistake, but it literally can't emit a malformed call. Hallucinating the syntax is impossible by construction. What the developer actually writes is a schema. Each tool has a name, a one-sentence description, and a JSON schema spec for its arguments, types, required fields, allowed enum values. The thing most beginners get wrong is treating that description as documentation. It isn't. The model reads it. The description is the prompt the model uses to decide whether this tool is the right one for the user's question. Vague description equals wrong tool picked. Specific, distinctive descriptions, including when to use it and when not to, make the difference between a tool the model uses well and one it ignores. Treat the tool list as part of the system prompt, because from the model's perspective, that's exactly what it is. Real tasks rarely take one tool call. The model might search a database, get a list of results, decide which one is relevant, fetch its full contents, and only then write the answer. That's multi-step tool use. The runtime keeps looping, feeding each result back into the context until the model finally produces a normal text response. That's how the model signals it's done. The complement is parallel tool use. Modern models can emit several tool calls at once when they're independent, fetching weather for 3 cities or running 3 database queries that don't depend on each other. The runtime executes them in parallel and returns all results in a single follow-up message. That single optimization can cut agent latency in half. Tools fail. APIs return errors, queries return nothing, networks time out. The instinct is to catch every error and retry inside the runtime. Don't. The model handles errors better than your retry loop will, because the model has the context. It knows what the user asked, what it was trying to do, and why the call might have failed. The right pattern is to return the error message as the tool result. The model reads it in the next turn and adapts. Retries with a corrected argument, falls back to a different tool, or tells the user it can't complete the request. Treat errors as more context, not as control flow. This single shift is what makes tool use feel intelligent instead of brittle. There's a small set of tools that almost every production agent ends up wiring up. Search, either keyword or vector retrieval over a private corpus, which is essentially RAG offered as a tool the model can choose to call. Fetch, pull a specific URL or document by ID. Code interpreter, run Python in a sandbox, useful for math, data parsing, plotting, anything where the model would otherwise have to compute step by step in its head. Shell access, run commands in a sandbox terminal, which is the foundation of every coding agent. And memory, read and write to a persistent store outside the context window so the agent can remember things across sessions. Different products combine these differently, but the toolbox doesn't change much. One pattern that's emerged across production systems: keep the tool count small. Fewer than 10 is a strong rule of thumb. The model has to read every tool's description on every turn, and a long tool list dilutes the model's ability to pick the right one. If you need more, group them behind a router tool, one tool whose only job is to delegate to the right specialist. Keeps the active list small without limiting what the agent can ultimately do. Until recently, every AI platform had its own way of registering tools. A tool you wrote for one agent didn't work in another. In 2024, Anthropic released an open protocol called MCP, Model Context Protocol, that standardizes the tool interface. A tool becomes a small server speaking MCP, and any model that supports the protocol can connect to it. OpenAI, Anthropic, Cursor, Claude Code, and a growing list of platforms all support MCP now. The effect is profound. Write a tool once, and every model can use it. The ecosystem has gone from fragmented integrations to a USB-C-like standard in under a year. If you're building tools today, build them as MCP servers. Tool use is the primitive. What you build with it is an agent, a system where the model operates in a loop, calls tools, observes results, decides what to do next, and works toward a goal across many turns instead of just answering one. Adding planning makes the agent decide a sequence of steps before executing. Adding persistent memory lets it remember context across sessions. The result is something that feels qualitatively different from a chat assistant. It can take actions in the world, recover from mistakes, and complete tasks that would be far too complex for a single prompt. That's the next concept in the stack. That's the end of this concept, but each video stacks on the last. Subscribe, and we add the next layer tomorrow. Up next, agents. How models plan, loop, recover, and complete real work end to end. Thanks for watching.